Hello, and welcome to another episode of the Book Club. We left off, we read 1.8 of Computer Organization and Design. So, let me just fire up Milton here. All right, there we go. So let's see here. We looked at the performance equations. So let's find that stuff. Oh yeah, then there were these power ones as well. Okay, so today we are going to be reading section 1.9, which is titled Real Stuff, Benchmarking the Intel Core i7. Each chapter has a section entitled Real Stuff that ties the concepts in the book with a computer you may use every day. These sections cover the technology underlying modern computers. For this first Real Stuff section, we look at how integrated circuits are manufactured and how performance and power are measured with the Intel Core i7 as the example. So it looks like we're going to be taking a look at the SPEC CPU Benchmark. It says a computer user who runs the same programs day in and day out would be the perfect candidate to evaluate a new computer. The set of programs run would form a workload. To evaluate two computer systems, a user would simply compare the execution time of the workload on the two computers. Most users, however, are not in this situation. Instead, they must rely on other methods that measure the performance of a candidate computer, hoping that the methods will reflect how well the computer will perform with the user's workload. This alternative is usually followed by evaluating the computer using a set of benchmarks, programs specifically chosen to measure performance. The benchmarks form a workload that the users hope will predict the performance of the actual workload. As we noted above, to make the common case fast, you first need to know accurately which case is common. So benchmarks play a critical role in computer architecture. SPEC stands for System Performance Evaluation Cooperative. It's an effort funded and supported by a number of computer vendors to create standard sets of benchmarks for modern computer systems. In 1989, SPEC originally created a benchmark set focusing on processor performance, which is now called SPEC 89, which has evolved through 5 generations. The latest, and I don't know if this is going to be accurate. I think this version of Computer Organization and Design, all they changed is risc-v, the architecture used within the book. I don't think they updated things, so I don't know if this is actually the latest SPEC benchmark. You could check. I'm not going to. But according to when this was published, it says the latest is SPEC CPU 2006, which consists of a set of 12 integer benchmarks, which is cint 2006, and 17 floating point benchmarks, which is the CFP 2006. The integer benchmarks vary from part of a C compiler to a chess program to a quantum computer simulation. The floating point benchmarks include structured grid codes for finite element modeling, particle method codes for molecular dynamics, and sparse linear algebra codes for fluid dynamics. Figure 1.18 describes the SPEC integer benchmarks and their execution time on the Intel Core i7 and shows the factors that explain execution time: instruction count, CPI, and clock cycle time. Note that CPI varies by more than a factor of 5. So let's take a moment here and look at the figure they talk about. So we've got a table here. I'll read the descriptions first. This is SPEC CPU2006. Benchmarks running on a 2.66 GHz Intel Core i7-920. As the equations on page 36 explains, execution time is the product of the three factors in this table: instruction count in billions, clocks per instruction, or CPI, and clock cycle time in nanoseconds. SPEC ratio is simply the reference time, which is supplied by SPEC, divided by the measured execution time. The single number quoted as SPEC CPU2006 is the geometric mean of the SPEC ratios. All right, so we have description, name, instruction count times 10 to the 9th, CPI, clock cycle time, which is seconds times 10 to the negative 9th. Then we have execution time in seconds, reference time in seconds, and the SPEC ratio, which, like we say, is a geometric mean. All right, so let's look through here. First of all, we've got interpreted string processing. The name is perl. The instruction count is 2,252, and again, this is times 10 to the 9th. The CPI is 0.6. The clock cycle time, and again, this is seconds times 10 to the negative 9th, it's 0.376. The execution time is 508 seconds. The reference time is 9,770 seconds. Wait a minute. So what's the reference time? Like, what are we referencing against? I don't know if did it say? I'm not sure if it said what the actual, what we're referencing against. But we really don't care, I guess. If you're curious, you could look it up. So, like I say, the reference time for this one was 9,770, and the SPEC ratio is 19.2. So that was for Perl. The next one is block sorting compression. They benchmarked BZIP2, and the instruction count was 2,390, which is, like around 100 more than Perl. The CPI is 0.7, so 0.10 more than it's like 0.1 greater than Perl for CPI, 0.376 for the clock cycle time, which is the same as Perl. Looking at this table, actually, all of them have 0.376 for clock cycle time. That's kind of interesting. Or because it's a 3.76 gigahertz processor, right? Is that what that is implying? I'm pretty sure, because this is clock cycle time. Like, it must be normalized to everything being 0.376. I don't know. I'd have to think about it more. We'll see. We'll read through this more and see if it clarifies things. But yeah, everything is 0.376 for the clock cycle time. Execution time of bzip2 was 629. Reference time was 9650. So the spec ratio is 15.4. Something interesting here is in this benchmark, the execution time of bzip was lower than perl. In the reference, the perl implementation, our perl benchmark, is faster for, like, perl is faster than bzip in the reference. And it's flipped in the actual execution here, so that's kind of interesting. So next up is the GNU-C compiler, GCC. Only 794 for instruction count, 1.2 CPI, 0.376 cycle time, of course, 358 for execution time, 8050 for the reference execution time, and a 22.5 spec ratio. Then we have a combinatorial optimization. The program is MCF, 221 instructions, and again times 10 to the 9th, 2.66 CPI. I'm just going to skip over the clock cycle time because we know they're all 0.376. 221 execution time, 9120 reference time, 41.2 is the spec ratio. The next one is a Go game, AI. The name of the program is Go, G-O. I'm assuming this is like a GNU Go implementation or something. It's 1,274 instructions, 1.10 CPI, 0.376, or yeah, I was going to skip that. 527 execution time. Oh wow, the reference time was 10,490, and the spec ratio is 19.9. The next thing we have is search gene sequence. The program is HMMER. 2,616 instructions, 0.6 CPI, 590 execution time, 9,330 reference time, 15.8 spec ratio. After that, we have Chess Game AI, and the program is SJENG, SJENG, I guess. 1948 instructions, 0.8 CPI, 586 execution time, 12,100 reference time, 20.7 spec ratio. Next up is the quantum computer simulation. It's libquantum. 659 instructions, 0.44 CPI, 109 execution time, 20,720 reference time, 190 is the spec ratio. Then we have video compression. It's H264 AVC. The instruction count is 3,793, 0.5 CPI, 713 execution time, 22,130 reference, and 31 is the spec ratio. Then we have a discrete event simulation library. It's Omnet PP. 367 instructions, 2.1 CPI, 290 execution time, 6,250 reference time, 21.5 spec ratio. After that is games / pathfinding, and it's A star. 1250 instructions, 1 CPI, 470 execution time, 7,020 reference time, 14.9 spec ratio. Then we have XML parsing. It's XALANC BMK, Zalanc BMK. It's 1,045 instructions, 0.7 CPI, 275 execution time, 6,090 reference time, 25.1 spec ratio. And then there's finally a row that says geometric mean, and it's only listed for the spec ratio, which is 25.7. So that was pretty boring reading through all those values in the table, but so to really understand performance, generally when we're thinking like instructions, generally the less instructions the better, although that's not always true because a longer sequence can be more efficient if there's less cycles for the instructions that are being run. And that's kind of the idea behind the RISC architecture, really, is, with a simple architecture, you might have more instructions, but if you, make those instructions very simple and fast, then you make up for the increase in instruction length, in the number of instructions run by having less cycles per instruction. So intuitively, a lower CPI would be better, right? Because the less cycles per instruction, that would be you're running faster, and kind of like as a rough metric, less instructions the better. So when we're just eyeballing these numbers, those are two things to think about. And then, so we have execution time, and we have a reference time. So there's the baseline that we're comparing against. And so okay, so spec ratio, it said, is the reference time divided by the measured execution time. Okay. So it's the spec ratio is basically just saying, how many times faster are you compared to the baseline. And then the geometric mean. So across all benchmarks, what we're saying is this processor is basically 25.7 times faster than the baseline there. But again, I don't know what the baseline is. And then if we really want to think about performance, we'd want to go back to our performance equations. So the useful ones are like instruction count times CPI divided by clock rate is equal to CPU time. CPU clock cycles is instructions times average clock cycles per instruction, or CPI. Looks like we also say CPU time is clock cycles times clock cycle time, or clock cycles divided by clock rate. So we had a clock cycle time listed. So when we're talking about clock cycle time, I believe we're referring to this number right here in this equation. So what we're saying is the inverse of the clock rate, right? So 1 over the clock rate is equal to 0.376 for this processor. And then it's times, it's seconds times 10 to the negative 9th. So I mean, if we just invert that again, if we say 1 divided by 0.376, so let me just, I'm going to do this on my phone here. 1 divided by 0.376. Okay, so that's 2.65. So, but this was seconds times 10 to the negative 9th. But I'm guessing, based on what my phone is telling me, it's like 2.6595 blah blah blah. So it's like a 2.66 gigahertz processor. I mean, I didn't do the units, so that's just a guess that's the unit, but that seems realistic. That the because we're benchmarking an i7, right? So, oh yeah, and it's said in the description of the figure. It says SPEC 2006 benchmarks running on a 2.66 gigahertz Intel Core i7 920. So yeah, I was correct that it's a 2.66 gigahertz processor, and that's why the clock cycle time is 0.376 for all of them. So to think about the performance, what we really think about for all of these would be, I think what we really want to think about is the CPU time. So we have the instruction count, we have the CPI, and we have the clock rate. So really, I don't know if the execution times listed here are from an actual like run of the benchmark, or if they're computed based on the instruction count, CPI, and clock cycle time. But we could compute the theoretical using that performance equation, although I suppose that would not be particularly accurate necessarily, because these might be, I don't know if this benchmark involves multi-threading, or there's all kinds of crazy optimizations that go on, and there's pipelining and all these things to consider that the basic equation we already looked at doesn't take into account. So the execution time is probably actually lower than what just doing the math would give us. So I want to actually just do the math for some of these, right? Let me open up my calculator again. Okay, so for example, let's take Perl. So we're going to say 2,252 instructions. That's times 10 to the 9th, but we're just going to go with the 2252 because whatever. So 2252 instructions. Let's see here. We're doing instruction count times CPI. So times 0.6. And then divided by the clock rate. So divide by 2.66. And we get a value of 507.9. The actual execution time listed in seconds on here was 508. So they either rounded it or it actually ran like a tenth of a second slower than the theoretical speed. I was hoping to find something different. I don't really want to do all these. Like, I don't want to really run through every one of these and see how they compare to the actual execution times, but I am curious, so I'm going to do another one here. This is bzip2, so I'm just putting in the information that I read off to you guys. If you want to follow along, you can take out your calculators and jot down, the values I listed. Or if you have a copy of the book, that would be easier. And you can do the calculations with me if you want. But if not, you're welcome to skip ahead if you're watching on the YouTube archive, of course. So let's see. So bzip 2390 times 0.7, and then we divide by 2.99. It should take 559.5. In reality, or wait, I did divided by 2.99. It's divided by 2.66 gigahertz. Should take 628.9. They listed 629. So again, off by 0.1. I'm wondering if they computed some of these values based on execution time or like working backwards, or if they took execution time, if they took these values and computed execution time like theoretically, or if they actually ran the benchmark. Like, I'm curious because we're getting values that are like pretty much exactly what it should be theoretically. And you'd expect, like, I was expecting the actual execution time would be better because our performance equation that we're using here doesn't take into account all kinds of things that processors do. Like pipelining and multi-threading and, all these fancy things, speculative execution. It doesn't take into account the cache, I would expect to see, if these benchmarks were taking advantage of the features of the processor, you'd expect to see performance better than the theoretical performance, because this performance equation is for like a single threaded thing without any of those fancy hardware optimizations, but we're getting results right in line with what the equation gives us. So I want to keep doing these. I know it's boring, but because like, are they really all going to be in line with what the theoretical tells us? So 794 times 1.2 divided by 2.66, 358.1, and they listed 358. So there's an example where it's actually 0.1 faster. So it rounded down. And like I say, I don't know if this is because the values listed in the table are rounded, or if it's an actual difference in execution time is just happens to be about 1/10 of a second consistently. I have a lot of questions. Okay, let's do the next one. So this is the combinatorial optimization program, which was MCF or something. 221 times 2.66. Oh wow, that had a CPI of 2.66, which is the just happens to be the speed of the processor. So we end up getting 221 because the 2.66 cancels for the execution time, and that is exactly what they had in the table there. So let's keep going. The Go program is 1274 times 1.1 divided by 2.66, 526.8. They listed 527. Again, they rounded up. Or if it's actually a difference, this one would actually be a difference of around 0.2 instead of 0.1. But still, everything is right in line with what you'd expect theoretically, which is not what I expected. Let's do the next one, 2616 times 0.6. So, I mean, I don't know, guys. What do you think? What do you guys think about this? I don't think anyone's actually watching right now, but I'm curious. So this gave me 590.0 and they put 590. I guess technically it would be, if I'm going to round, it would be 590.1 because it was 590.07. But anyway, very close again. So, I don't know about these benchmarks. Are these, like, I'm very skeptical what they're benchmarking. If these benchmarks are designed to benchmark the, like, single-threaded performance specifically, or if they are trying to take advantage of processor features. Because if you just take this table and do the math like I'm doing right now, it gives you the impression that the performance equation that we saw earlier in the book is a very accurate representation for real world code, despite the features of the processor. We're getting basically no difference, like a tenth of a second, which I guess matters, but a tenth of a second, that does matter, but for all I know, these values are just rounded in the table, so is it actually a difference at all? So 1948, and I mean, I'm sure when it gets deeper into the book and we're looking at the more complicated things, it'll have some things to teach us, but I don't know. I feel kind of misled by this table. The next one, I got 585.8. They had 586. Like, just reading through this book linearly, right now what we've learned is we've learned a performance equation, and looking at a benchmark, we're being told that basically that performance equation will give you the actual execution time, which for like a modern processor like an i7, which I don't think is right, but that's what the numbers are telling us. So let's keep going. 659 times 0.44 divided by 2.66, 109, and they had 109. Okay, 3793 times 0.5 divided by 2.66, 712.9, they had 713. Okay, just 3 more to go, guys. 367 times 2.1 divided by 2.66, 289.7. They had 290. So it really seems like they just rounded the numbers, and that this benchmark, either the values in this table, some of the values, like they might have taken the execution time and then worked backwards from it to get certain values, in which case it makes sense that working forward we end up getting the result that they have in the table. Okay, 1250 times 1 divided by 2.66, 469.9, they had 470, 1045 times 0.7 divided by 2.66, 275, and they had 275. So yeah, all the math checks out. I took the time and did the math for every single benchmark, and all of it matched the actual execution time. So that's an interesting observation, to say the least. But let's keep reading and see what it has to say about the table. So figure 1.18 describes the SPEC integer benchmarks and their execution time on the Intel Core i7. It shows the factors that explain execution time, instruction count, CPI, and clock cycle time. Note that CPI varies by more than a factor of 5. So yeah, CPI does vary quite a bit. To simplify the marketing of computers, SPEC decided to report a single number summarizing all 12 integer benchmarks, which I guess was that geometric mean. Dividing the execution time of a reference processor by the execution time of the evaluated computer normalizes the execution time measurements. This normalization yields a measure called the SPEC ratio, which has the advantage that bigger numeric results indicate faster performance. That is, the SPEC ratio is the inverse of execution time. A CIENT 2006 or a CFP 2006 summary measurement is obtained by taking the geometric mean of the SPEC ratios. Here's an elaboration. When comparing two computers using SPEC ratios, apply the geometric mean so that it gives the same relative answer no matter what computer is used to normalize the results. If we average the normalized execution time values with an arithmetic mean, the results would vary depending on the computer we chose as the reference. Okay, so they make a distinction between geometric mean and the arithmetic mean. The formula for the geometric mean is nth roots. There is a pi symbol with I equals 1 and n at the top. Now, what's a pi in math? I know a sigma is a sum. Is pi like multiplication? Yeah. Or wait. I mean, oh yeah, it says right below it, pi means the product. So it's saying the execution time ratios, you multiply them all together, and then you take the nth root. And that is what the geometric mean is. So I'm still in the process of like studying statistics on my own. I never took like a proper statistics course, and I'm just like reading Wikipedia pages. So I don't know the advantages of a geometric mean, so to speak, or, like the intuition behind a geometric mean. But anyway, they use the geometric mean. And it says that if we use like the normal definition of a mean, the results would vary depending on the computer we choose as the reference. Whereas this way, no matter what you use, you'll get the same relative answer. So that's the intuition behind it. To really understand that, we need to like dive deep into the math and, statistics and stuff, which we're not going to do right now. I'll probably go over that on stream at some point. But anyway, let's keep reading here. So SPEC power benchmark. Given the increasing importance of energy and power, SPEC added a benchmark to measure power. It reports power consumption of servers at different workload levels divided into 10% increments over a period of time. Figure 1.19 shows the results for a server using Intel Nehalem processors, similar to the above. So it says here, SPEC Power SSJ 2008, running on a dual socket 2.66 GHz Intel Xeon X5650 with 16 gigabytes of DRAM and one 100 gigabyte SSD. So we have target load percent performance, which is SSJ ops, and then average power, which is watts. So we have 100% load. Oh, okay, and they go in 10% increments. So at the top is 100% and it goes down to 0% at the bottom. We have 865,618 performance and 258 watts. Then at 90%, we have 786,688 performance and 242 watts. At 80%, we have 698,051 performance, 224 watts. And at 70%, we have 607,826 performance, 204 watts. Let's see, I just did 70%, right? 60%, 521,391 performance, 185 watts. At 50%, we have 436,757 and 170 watts. At 40%, we have 345,919 and 157 watts. At 30%, we have 262,071 and we have 146 watts. At 20%, we have 176,061 and 135 watts. At 10%, we have 86,784 and 121 watts. At 0%, we have 0 for performance, but we have 80 watts. The overall sum is 4,787,166 for performance and 1,922 for watts. And then they take the sum of the performance divided by the sum of the power, and that value is 2,490. So looking at these numbers, it seems that the power, interestingly, at a target load of 0%, we're using 80 watts, and then it just scales up the higher the load, the more the power, right? That seems pretty straightforward. And performance, it looks like the same exact kind of relationship with the performance. I don't know what SSJ ops means. I don't know what this metric is, but I understand watts. So where's our performance equation here for power? Okay, so we had a pulse is energy is the capacitive load times the voltage squared. Our energy is proportional to. That's what that symbol means, if I remember correctly. So for a single transition, it's just half that. And so we say power is single transition times the frequency switched. But that doesn't really relate to the benchmark here. So we can't really run the numbers like we did with the last one. So let's continue reading then. SPEC Power started with another SPEC benchmark for Java business applications, SPEC JBB2005, which exercises the processors, caches, and main memory, as well as the Java virtual machine, compiler, garbage collector, and pieces of the operating system. Performance is measured in throughput, and the units are business operations per second. Once again, to simplify the marketing of computers, SPEC boils these numbers down to one number called overall SSJ ops per watt. The formula for this single summarizing metric is overall SSJ ops per watt equals sum of SSJ ops divided by sum of power. And it goes from 0 to 10 in the sigmas, and that's because it would be 10% increments, right? So it says where SSJ ops, and they have I as a, what do you call it? Like, I'm having a memory blank, where you have the little number above, like if it's a power, but here, it's where it's below. My mind is blanking on the term for both of those at the moment. But anyway, the ith SSJ ops is performance at each 10% increment, and the ith power is power consumed at each performance level. Okay, so I've still got time, not a ton of time though. Let me see here. We could read 1.10. Let me see how long 1.10 is. It's a couple pages long. I don't know if we want to get into that right now. Okay, so section 1.10 is fallacies and pitfalls. And then after that, we have 1.11, which is concluding remarks. 1.12 is historical perspective and further reading, which is just like a little paragraph or 2 paragraphs. And then 1.13 is exercises. And after that, I believe, is answers to the check yourself. And then we'll be moving on to chapter 2. So I think we will leave that for next week. So thank you everyone who tuned in today, if anyone did. And thank you everyone who watches on the YouTube archive, which is available at risc-v. You can follow me at HMN_risky on Twitter to get updates about the series. And if you would like to support the series, my Patreon can be reached at patreon.risky.tv. I will see you in the next episode, and stay risky, everyone.